Well, good morning, everybody. It's nice to see people tuning in here. I see lots of comments in the chat already, people talking to each other about the amazing weather that we're having outside, which is fantastic. It is not yet 11 o'clock, so we're not going to start anything kind of too official just yet, but I am going to post a question that people can kind of start working on, and it'll be like something to think about while people are joining us. So I'm going to go ahead and present this question. There we go. And so hopefully you see that on your screens. There we go. In the meantime, while people are filing in, please feel free to say hi to each other. Say hi to me in the chat. That is all good. Lots of people appreciating how it's a nice day. I thought about closing the blinds behind me in order to have less backlighting, but I couldn't do it. I couldn't bring myself to not have all of this beautiful natural light shining in. It's funny, I have a friend who is from here and who works in the UAE, and actually one of the folks in our class is from the UAE, and he said that he was talking with some of his colleagues there, and they didn't understand why all the Canadians they knew spent so much time talking about the weather, and then they kind of got to see each other's perspectives when he lived there for a while, and the weather was like almost always sunny. not always. And they got to see his perspective when they would fly into various places in Canada. So he flies for an airline. And they'd fly into various places in an airline, and bad weather means that nothing happens for 3 days. And so it was kind of interesting that they got to share each other's perspectives on that. But yes, we do talk a lot about the weather here, but often that's because it's quite consequential. And it was kind of fun on the weekend where if that system coming through had tipped a little bit this way or a little bit that way, it made a huge difference as to whether we were going to get a massive blizzard and everything be shut down for a day or two or not. So, all right, folks saying hello to each other in the chat, etc. That's lovely. And people are also starting to answer the question. So today we are not going to have a lecture in the sense of me going through slides. I thought I would use this time to do a tutorial kind of thing. And so we will look at some examples and some practical guided examples of how we can design algorithms that use loops, because that's a pretty core piece of what we need to be able to do in this course. And in fact, as we get closer to 11, I'll even say things that are a little more official now. So this is often a part of the course where those who have been kind of doing all the exercises along with as they've been given, kind of say, all right, this material is changing and it's maybe getting a little more interesting. But those who have not been doing the exercises, this is sometimes a point in the course where the wheels start to come off a little bit. We are now moving past things that can be purely explained in terms of like mathematical expressions, and we're moving into things that are much more definitively algorithms, where we need to think a lot about how does the computer see this or that. And so it is really, really important that we continue following along with all the exercises and the examples and doing the exercises. And now we're going to start submitting assignment work as well. And actually, sorry, I should have the top hat question up while I'm talking, shouldn't I? So this is just kind of an introductory. If you're just joining us at 11, then this is just a question to get you thinking as we start today's tutorial. So today we're going to have a tutorial, and I'm going to show you some things about, in practical terms, how we actually design algorithms that use loops. And this is where we really start to get into kind of the meat of the course. So there was a bit of an introduction, a bit of a taster. Now we're really getting into some of the core material. And so this stuff is really important, so please do all of the exercises, work through it. If you don't understand them, talk to me, talk to your friends, talk to the tutors in the Eng1 Success Center, talk to the SI leader, talk to Ms. Hogan, talk to the TAs who are in the labs. There are so many people who are here to help you. And so we would really love to be able to do that. So if there's anything that you're not clear on, now would be a really, really good time to start engaging with us to try to figure it out. Because if you leave it past this point, then you may find it harder and harder to be able to catch up. So if you're sitting at home and you say, I'm not sure, I don't know if I know what I'm doing here, that's okay. Reach out and we will figure out how to get you connected and figure out what is being misunderstood and get you on that right path. So it's not at all too late. But if you're at home saying, this all looks really easy, I'm not going to bother to do the exercises, I'm sure I'll be able to do it if I need to, and you're not doing any of the work yourself, well, when we get a little bit past here, you may find that things start to get a bit tricky. Someone says, can't see the whole question. Yes, so I will... actually, as far down as print wibble is the end of the question. So I can shrink it this way, but then it's even kind of harder to see. Well, yeah, no, then you can't see the bottom at all. So the user is entering, they're typing 1, they're typing 0, they're pressing enter when they are prompted, and then tell us what the program does. Oh, the Facecam is blocking. Yes. I hear what you're saying. Who needs to see that face, huh? All right. So as people are answering this question, I will close that in just a few seconds. Okay, someone's pointing out in the chat that I said I would change the question on the missing increment, but I haven't changed it yet. Okay, yes, that is an excellent point. I changed another one recently that was incorrect because I had changed some things about the question, so I also needed to change some things about the answer, but it looks like maybe I forgot to do the one which is the missing increment. And so I'll make a note of that here now. All right, so that question is almost done. And lots of people have answered it, so I'm going to go ahead and close that question now. And we'll take a look at the responses that came in. Okay, and so there were a few different ideas about what the correct answer is. So, okay, this is good. We're working through these problems, and we're going to see what they... how the computer handles all this stuff. So why don't we pop open Thonny so that we can write this code and sample.py. I will save that under tutorials. Okay, so let's first of all, start by typing in this same code. So int input number, there we go, if x is greater than or equal to 17. By the way, why do I have this? Why am I taking, oh, there's a syntax error. I'm taking the result that comes back from input. So input's a function, we call a function, we pass an input into it, it can return an output. We take the output of input, we take the output of this function, we pass it to int. Why am I passing it to the int function? Why would I want to do that? Right, because we can't use a string for calculations. So if x is the string 1, 0, well, I'm not going to really be able to compare that to the number 17. So I want it to actually be a number. So if x is greater than or equal to 17, we print foo. And we divide x by 2. Elif. So because this is elif, we could take this condition. If we do, we will not even bother looking at this condition. So if this is true, we're definitely not going to do this stuff. So if x is greater than 5, we'll print bar. And we'll multiply x by 4. Then if x is greater than 15, if, not elif, it says, we'll print baz, and else print wibble. So out of if x is greater than or equal to 17, here's some stuff. elif x is greater than 5, here's some stuff. Out of these two alternatives, how many of those alternatives could we take? We could go in here and do some stuff. We could go in here and do some stuff. And by do some stuff, I mean execute some statements. So what is the maximum number of alternatives that we could visit by going into this if statement? And what's the minimum number of alternatives? A couple of people are typing. Right, 0 or 1. Good. So when we get to this if statement, if this condition is true, we will execute these statements. And then we'll be done. We go right to the end of the if statement. Do not pass go. If this condition is false, but this condition is true, then we might go in here and execute these statements. So if, elif, this if statement has no else clause, which means it's possible if x is not greater than or equal to 17 and x is not greater than 5, so let's say x is negative 2 or something, well then we're not going to execute these statements or these statements. So we might execute one of those blocks of statements, or we might execute 0 blocks of statements. How about with this if statement on lines 11 through 15? How many blocks of statements will we execute there when we execute that if statement? Right, so the answer now is exactly 1. We are definitely going to execute either this block of statements or this block of statements, because if this condition is false, we don't execute this block of statements, but we have an else. So that catches any other possibilities. Good. So let us debug this script one step at a time. So first of all, let's click on or press F6 for step over, and it prompts me for a number. And I said in the problem formulation, type 1 and then 0 and press enter. And then that indeed got converted to an integer. In fact, let's do that a little more slowly, not to belabor too much, but step into. So we have to evaluate this expression. So line 1 is an assignment statement. Variable on the left, expression on the right. So we have to evaluate the expression on the right. So how do we do that? Well, inside a function call takes precedence over other kinds of operations, and it looks like function calls are all we have anyway. So we are going to step into this function call. How do we call an int function? Well, we take whatever its input is. Well, we have to figure out what its input is. Its input is the result of another function. How do we figure out what that is? Well, we call the input function, we pass the prompt number, which is a string, into input, and that causes a prompt to be generated for the user. I press 1, I press 0, I press enter, and now that expression, input number, that whole expression evaluates to whatever I typed in, which is the string 1, 0. So I take that string 1, 0, I pass it to the int function, and look at that, it results in the integer 10. Okay, now we are going to look at this first if statement. So if x is greater than or equal to 17, so we check this condition. And the way that we check the condition is not by trying to remember what was just typed in by the user for the value of x. No, we check by looking in the box. So we look in the computer's memory and say, here's a place that's supposed to store a value. We're calling that variable x. What's currently in that variable? And the answer is 10. So is 10 greater than or equal to 17? No, it's not. So this is going to evaluate to false. So if false, well, we don't do that. Instead, we can check the next condition. If this condition doesn't work out, we can check the next one, elif something. So elif x is greater than 5. So is x greater than 5? Well, how do we know what x is? Well, we check the computer's memory. We look in the box. So x is whatever was over here, which is 10. Is 10 greater than 5? Yes, it is. So this is going to evaluate to true. The expression 10 is greater than 5 will evaluate to true. And so we go in and we execute these statements. So we print bar. So bar does get printed. And then we have an assignment statement. So x is assigned by x times 4. Now in math, you can't say x is equal to 4x unless x is 0. But in programming, an assignment statement, this is perfectly fine. It says whatever value you get by evaluating the expression on the right, store it in the variable on the left. So x times 4. What is x? Well, let's go look in the computer's memory. It's 10. 10 times 4 is 40. And so 40 gets stored in x. Now when we execute the next block of statements, we should not be thinking about, we should not be trying to remember, okay, what was the value of x before, and then what did it get changed to, and what is an expression that represents the current value of x in terms of all of its previous versions. You can sort of, you're clever people, so you could do that kind of thing if we only change x once or twice or 3 times or maybe 4 times. But if the value of x gets updated 1,000 times or 1,000,000 times, which is super common in programming, right? In programming, 1,000,000 is a small number. So if we have 1,000,000 times that we're modifying x, we don't want to try to keep all that in our head. No, what we want to do is do what the computer does. Look at the place in memory where we're storing that variable x. So is x greater than 15? Well, we're going to go check. X in memory is 40. So is 40 greater than 15? That's an expression which evaluates to true. And if true, then we're going to print baz. Because this condition was true, we're not going to execute the else, which means we print bar and baz. So that is, or those two are the most common responses, but there were some other answers that came in. So if that stuff doesn't quite make sense, then you might want to run that again through Thonny, or maybe we can chat, or maybe you can chat with a help center tutor or a TA or your friends, somebody. But you want to figure out why it is that you didn't quite get the right answer, see why it was, and so that you can get the right answer in the future. Okay, there's a question here. Why didn't the Python use x equals x divided by 4? Why wasn't it divided? Well, because this is just an arbitrary exercise that I set. So it's kind of like, why did the math problem use plus instead of minus? Well, I don't know, because that's the problem that was set. This is not meant to represent any specific algorithm for doing any real world thing. This is purely just a little exercise to see if you can trace through the control flow in the same way that the computer does. Someone says, if we had an input greater than 17 in the first place, it should have different answers. Yeah, absolutely. If we put a different value into this algorithm, we'll definitely get a different result. If we have a result that is greater than or equal to 17, we will end up with a different result. And then we may also change the result if we have a value that is greater than 30. Because if you have a value that's greater than 30, then this will be greater than 15. So that'll change this behavior as well. Okay, good. Now, let me ask you another thing. And this is a quicker thing. Hopefully this will only take a second. And this is, again, not that there's a right answer here, but I am just quite curious about how these things are developing as people move to St. John's, etc. Someone said, if we had an input greater than 17 in the first place, you should have different answers, so there's no one right answer. In the question, I said, if the user types 10 in response to the input. So there's a right answer for a specific input. And again, if you missed that question, it'll be posted online after. Okay, we've got answers coming in. I'm going to close this one in just a few seconds. Let's call it in 5, 4, 3, 2, 1, and close. Okay. All right. So we've got a few people here, a few people there, a few people there, but the plurality of responses are in the library and in St. John's, and a few people in other places on campus that weren't mentioned. Okay, good. Again, there's definitely no right answer there or anything, but just curious for my own information, how things are developing. Okay, so today we are going to continue doing things that are related to what we were talking about last time, and we're going to have a little bit of a tutorial. So we're going to talk more about how we design solutions to problems using loops. So you will recall, hopefully, that last time we were talking about a while loop. It is called a while loop because it uses the keyword while. So if you took an if statement that had no else and you changed the word if to while, then it would kind of mean almost the same thing, but the difference is that if you say if condition, do some stuff, then you do that stuff 0 or 1 times. If you have a while loop, so while condition, do some stuff, well, then you do that stuff 0 or more times. You could do it many times. So we introduced some new syntax when we did that. So we introduced the keyword while. We introduced the keyword break. What does break mean? Kind of does what it says on the tin. But what does break mean? Anybody recall the break keyword? Oh, there's some typing happening now. Right, we break out of the loop. So if we were going around and around and around in a loop, then it says, all right, we're done now. So we just stop executing the loop and we go to, as somebody pointed out, the next line of code after the loop. So we move to the next statement after that loop. The while loop also, we have another new keyword, which we didn't actually talk about, but I'll mention it now. That while that additional keyword, which you may find helpful, is continue. So continue is a bit like break, but instead of breaking out of the loop, you just stop with the current iteration through the loop and go back to the top. So we had, let's see. So we had something that looked like this as an example, and I could say here, if I type the word continue, then what's going to happen? Well, as we execute this loop, if digital read returns something false, therefore not digital read is true, we read a light value, and then when I get to continue, it says don't break out of the loop completely, but do stop this iteration of the loop. So don't go down here, don't do those statements, just go, as soon as you hit continue, go immediately back to checking the condition and going around the loop again. So we saw the break keyword last time, and the continue keyword is kind of a bit like it. So those were new keywords, but again, in some ways it is a lot like an if statement because we have kind of similar syntax and we still have a Boolean expression. The more complicated thing is that we might now check that condition many times, and inside of the loop, that condition may change. So we may, for example, we might say something like, well, as long as x is greater than 10, I want to keep going around that loop. And inside the loop, we might be doing something that's changing the value of x, increasing it, decreasing it, which means the next time we go to check, we don't want to just remember what was x originally. We want to look at what is the current value of x in the computer's memory. If we have a loop that doesn't change that value, that condition, then we may end up accidentally writing an infinite loop. The reason that this is a hyperlink, by the way, is just because infinite loop is also, in fact, a street in Cupertino, California. Infinite loop is a street where Apple's old headquarters is, which they got to name the street, apparently, because when you own that much land, I guess you get to name things. And so they named the street Infinite Loop because they thought it would be a fun joke. Programmers love puns. Okay, so we saw new keywords. We saw that we have a condition, which is still just a Boolean expression, and we saw that it's kind of easy to write an infinite loop by accident. If you wanted to write an infinite loop on purpose, if you wanted to write a loop that would never stop, maybe that loop does something like, well, in an industrial control setting, for example, read the pressure from this valve, and if the pressure is greater than something, turn the thing off, otherwise go check it again. And we just want that loop to continue forever, or as long as the piece of equipment is turned on, and we never want that loop to stop. How can we make it really clear and explicit? How would we write an infinite loop on purpose? What would that look like? So if instead of making this loop continue as long as I'm holding down or as long as I'm not pressing the digital read button, how could I make this loop be an infinite one? Yeah, there we go. Change the condition to just true. And I think I did this at one point when we were talking about things in the last lecture. So while true evaluates to true, well, true is always going to evaluate to true. So this is saying nice and clearly and explicitly so that anybody who looks at the code says, they meant for this to be an infinite loop. It's not an accidental infinite loop. It's a deliberate one. Good. Someone asked, could I explain continue again? Yes, absolutely. So break means that we are going to leave this loop. So let me write something different. So let's say, okay, let us say that I have while true, grade is equal to input, enter your grade. And then let's say that I want to compare that. So, and this is actually related to an exercise that I gave you previously that I said could, with conditional control flow and piecewise functions and using if statements, could you write some code that would accept a grade and then tell me what the letter grade is? So if the grade is greater than or equal to 80, then I'm going to print A. If the grade is greater than or equal to 65, I'm going to print B. If grade is greater than or equal to 55, print C. If grade is greater than or equal to 50, print D. Else, print F. Okay. So there's a flaw with this code. What is that flaw? What's the problem with the code that I've just written? Right. So input here gives me a string. Input always returns a string. If I want to go comparing strings with integers, if I want to check is the grade 97 greater than or equal to 80, we're going to find that doesn't really work. We're just going to get an error. So I do indeed need to convert to int. Now, did I need to say here if grade is greater than or equal to 65 and grade is less than 80? I could write that. Do I need the extra and grade is less than 80 part? No, I don't. Why not? Yeah, maybe I just should have said why don't I rather than do I. Why don't I need this extra part, this and grade is less than 80? Right, because we have this if else construction, which means that if this condition is true, then we will only execute these statements and skip all the other ones. And if we skip all the other ones, that means that we're not going to check this condition. So by virtue of the fact that we are even checking this condition, we know that grade must be less than 80 because we know that this condition was not true. So we don't need to have those two extra parts. Incidentally, by the way, if you're interested, you could, in fact, in Python, just write this. You could write if 65 is less than or equal to grade, which is less than 80. So you could put grade in the middle of that range. Some programming languages, that expression actually doesn't work. It evaluates something that you wouldn't expect, but in Python it does. However, we don't need it because we already know that grade is less than 80. Okay, so if I run this program over and over and over, I'll enter the grade 97, and I'll enter the grade 47, and 85, and 96, and 63, and 67, and we're covering off, I think we've got all the grades here, 51. There you go. So these are all pretty okay grades, but, well, what do I do when I'm done? Okay, so I can enter an empty line, but now we get this really ugly error, right? So I would rather not have a really ugly error. I would like to be able to cleanly tell the program, I'm all done. I have no more grades to enter. So what I could do is I could check if grade, well, actually, so I could, in fact, take that string input and say, if the grade is equal to the empty string, then we will do something. Otherwise, convert it to an integer. So let's say that I want to stop running my little program whenever the user enters the empty string. Or even better, let's say I want them to type quit. So if the user types quit, then I should quit my program. So what should I use? What should I type? Someone says, beware of the elif. Yes, beware of elifs. They are subtle and quick to anger. Yes, I'm going to use the break keyword. Very good. Okay. Now, so I can now run my program and again enter 89, 42, 76, and then I'll type quit. And the program ends, and it ends nicely and cleanly with no errors, so that's good. Let's say, though, I want to handle the case of somebody accidentally presses enter, and they didn't mean to press enter, but they did, and I don't want the whole program to explode. I don't want to have an error. I don't want the program to quit. But I also don't want to convert their input to a number and try to compare it to a grade. I just want to go back around and try again, get the user to try again. Well, in that case, I could check that if grade is equal to the empty string, this is a place where I could use the continue keyword. So in this case, I'm going to run the script and I'm going to type 99, and let's hope we get lots of those in the course. And then if I press enter, notice now, if grade is equal to the empty string, I continue, which means that I don't run anything else in the loop. I just go back around to the top of the loop and start running the next iteration of the loop again. I check the condition and then I run the loop, which means I can press enter as many times as I like here before I start entering numbers again. And when I'm all done, then I can press quit. So that's what the continue keyword is useful for. We kind of break out of the current iteration of the loop and go back around to the top, check the condition, and then if it's still true, go through the loop more. Okay, good question. Thank you. Okay, but now let me ask you something else, and I will ask you this as a top hat question. So, future engineers who have done some mathematics in your life, tell me, what is, and I'm asking this as a top hat question, what is the factorial of 7? You may have to think, ooh, factorial. I remember that was a thing I learned once upon a time. Or perhaps it isn't, but if you didn't, you'll learn it now. So, folks answering, this is good. Answers coming in. All right, I'll give this just another few seconds. And we'll close this in 5, 4, 3, 2, 1. Close. Okay. And so we had the answers were, all right, we had a few different answers, but mostly 5,040, which is in fact the correct answer. So good job. So what is a factorial? Someone's getting ahead of the game here and typing in Python code already. We're not there just yet. I mean, that's good. That's good that you can do that, but we're not quite there yet. Okay, so I said, what is 7 factorial? And someone said 7 exclamation mark. Yep, that's good. But what is a factorial? What's the meaning of factorial? So it's clear that you have some understanding of it because most people were able to get the right answer and tell me what the factorial of 7 actually was. But what does it mean? Yeah, okay. So we've got 7 exclamation mark emoji. Very good. So one person typed in 7, bold 6, not bold 5, bold 4, not bold 3. That's because of the formatting of Top Hat. So I know that you were typing 7 asterisk 6 asterisk 5. So yeah, good. So we're multiplying all of these values from 7 down to 1. Okay, good. So some concrete examples. The factorial of 3 is 3 times 2 times 1. The factorial of 5 is 5 times 4 times 3 times 2 times 1. Okay, very good. But can we come up with a slightly more abstract definition of factorial? So rather than just putting it in terms of examples, is there a more... If I told you that I wanted to find the factorial of n, how would you find the factorial of n? Where n could be any number. Yep, someone else typed in 7 times 6 times 5 times 4 times 3. Yep, that's good. In terms of n, okay, so multiply all factors. Well, it's not factors, and 7 only has 2 factors, being 1 and 7. But, okay, we multiply every integer from 1 to n. Yep, so that's a good way of putting it. Or another way of putting it is to multiply n times n minus 1 times n minus 2 times n minus 3 and so on. Okay, good. So one way to define, and there's more than one way to solve every meaningful problem really, but there's more than one way to define the factorial, but the definition we're going to use is, well, here's part of it anyway. So we're going to say that n factorial is n times n minus 1 factorial. So, in that case, what is the factorial of 3? So the factorial of 3, by this definition, is 3 times 2 factorial. And, oops, sorry, let me get my little whiteboard open. There we go. That's the screen I meant to use, sorry. So the factorial of 3 would be, oh, no, you can't see that. Let me draw that in a different place. 3 factorial is equal to 3 times 2 factorial. Well, what's 2 factorial? 2 factorial would be 2 times 1 factorial. Very good. What's 1 factorial? It'll be 1 times 0 factorial. And then, let's see, 0 factorial would be what? 0 times negative 1 factorial. And what's negative 1 factorial? Well, it would be negative 1 times negative 2 No, wait a minute. Something's gone wrong here. What's gone wrong with this definition? So I've given half of a definition is the problem, right? So whenever we deal with recursion, where something of n depends on n, then we need more than just this part of the definition. This covers almost every case. For almost any value of n, this is very useful, but we also need a base case. We need to know when to stop. So n factor, oh, sorry. Keep forgetting which thing I'm gesturing at. So we need more than just this definition that I have here. We also need this part of the definition. So that means that where we went wrong was in all of this stuff where we got past, well, what is 0 factorial? So 0 factorial is not defined in terms of negative 1, in terms of negative 1 factorial. 0 factorial is just defined to be 1. So 0 factorial is 1. Why? Because that's what the definition says. So it's not, there's no rationale based in anything else. It's just the definition of the factorial. Good. So with that information, let's think about, and another way to put that, by the way, is if we think about like a piecewise definition, we can say n factorial is either n times n minus 1, as long as n is greater than 0, or n factorial is just 1 if n is equal to 0. Okay. So that is kind of the definition, but now how can we take that mathematical definition? We've thought through a couple of examples, and that's always a good practice. When you have a new problem that you need to figure out how to translate into code, don't start by thinking about what is the Python code that solves this problem. Start by saying, how do I solve this problem? And you don't really know how you solve this problem until you, in fact, solve it a couple of times. So you need to think through some of the details yourself. And personally, I find, and I think it is often a very good idea for students in 1020, when I give you a problem that says design an algorithm to do blah, the first thing you should do is just do blah by yourself. Do it by hand. Try to solve the problem mathematically, and then you can look at, and especially if you do it in 2 or 3 times in 2 or 3 different ways, and you can take a step back and say, okay, so what is it that I actually did there? Some of these problems that I'm going to be giving you on things like the midterm next Tuesday, some of these problems are going to be things where if I were asking you to do them by hand, you'd say, oh, that's so easy that I don't even have to think about it. Well, the problem is we need you to think about it because you have to teach the computer how to think about it, which means you need to look at the thing that you can do just like almost automatically and then break it down into smaller steps for the computer to understand. So how are we going to think about how to design an algorithm to compute the factorial of n, where n could be absolutely any number, well, any positive integer, I guess we should say. So I hope it's clear that we're going to need some kind of a loop because we have something that's happening over and over and over again. We're multiplying this by that, by that, by that, by that, by that. So there's going to be, we can't just write an expression. We can't just write an expression which is n times n minus 1 times n minus 2 times n minus 3 because we don't know how far we need to go. So we are going to have some kind of a loop that is doing multiplications over and over and over again. So here's a couple of helpful design principles for designing algorithms that involve loops. One is we want to start with the common case. So there are a bunch of things that we're going to need to think about. How does this loop get started? When do we know that we're finished? What's the stuff that we have to do in the middle? My recommendation to you, and this is my recommendation to me too, so it's not just for you, is that we want to start by thinking about the common case. What is it that we need to do over and over and over? Don't worry so much about how the loop gets started. Don't worry yet about how it finishes, but just think about what's the thing that we're going to have to do 10 times, 100 times, 1,000 times, 1,000,000 times. What does one step look like if we have to do this in 1,000 different steps? So in our case, it's going to have something to do with multiplying a number by another number. And so there's going to be some kind of multiplication that we do lots and lots and lots and lots of times. This is kind of like any sort of design, right? When you are designing any kind of system, or if you're designing any kind of physical thing that's going to be built, it is important to think about manufacturability, right? Are you designing something that can actually be made? It is important to think about end of life cycle, so that, you know, if you're building a system to save the environment, but disposing of that system at the end of its life is extremely environmentally dangerous and deadly or toxic and whatever, well, maybe we haven't gained anything. So we do need to think about how do things get started and how do things finish up, but we don't start there. We start by thinking about what is the common use case of this thing that's going to happen every single day. Commissioning a building is a big, long, complicated process, but you don't design a building by starting thinking about commissioning. You start designing a building by thinking about what are people going to do in that building every single day, and think about those things first. So similarly, when we're designing programming, we're going to start with the common case. So when I have a factorial that I'm attempting to compute, so let's look at so we had this example of 5, right? So I said 5 factorial is equal to 5 times 4 times 3 times 2 times 1. Okay, so forget about the beginning, right? And forget about the end. But let's just think in the middle. What is the thing, what are the steps that we are repeating over and over again? If I had to tell you what is the kind of the core essence of this factorial algorithm going to be, a step that gets repeated, and it gets repeated more times for bigger numbers and fewer times for smaller numbers. What is it that we're repeating over and over? Okay, so there is some kind of a subtraction operation that's happening here, someone pointed out. Yes, good. So we are subtracting 1 from something. And it was suggested that that might be n minus 1. Okay, good. What else? So we might have some kind of a loop that says, for example, n becomes n minus 1. Yep, okay, that's a good thing. But that's not all. We need more than that to compute a factorial. Right, there needs to be a multiplication. Yeah, there we go. And, oh, it looks like several people said that at basically the same time, so that's good. So we need to have something is n times something. Okay, so now let's think about, let's assume that all of the previous iterations of the loop did their job correctly, and all the subsequent iterations of the loop are going to do their job correctly. But on one iteration, what's the thing that needs to happen each time? So if we have some value, and let's call it f. So let's say that f is the factorial that we have computed thus far. So we've been doing some work to compute some portion of this factorial. So we are now going to, what do we need to multiply n by? So if we are currently here at the number 3, so if n is equal to 3, then what is it that we need to multiply n by and store in f? Okay, so there are, I should probably point out, by the way, people might be thinking about this differently, because even in the way I've formulated the problem here, there's a couple of different ways we could think about it. We could think about ourselves as starting up here and then moving down, or we could think of ourselves as starting down here and moving up. So I'm going to suggest to us that, just so that we are all on the same page, let's assume that this is the starting point. Oops. Let's assume that we started with the big number, and every time we go through this loop, we are going to, so at this point, we've already got, at this point, when we get to n equals 3, I'm going to say that f is already 20. So we are going to multiply n times f and assign that into f, which means at this point, f will become 60. And then we're going to subtract 1 from n, which means, so let me draw that slightly differently. Let's say that when we get to this point in our loop, we have a value of f, which is already 20, and we have a value of n, which is 3. So we are going to multiply n times f, so 3 times 20, That will give us 60, and we'll store that in f. And then we are going to subtract 1 from n. So n minus 1 is 3 minus 1. That gives us 2, and we're going to store that in n. At which point, we are now here and ready to move on to the next step. So each individual step, we're going to assume that everything before us was right, and we're going to assume that we've taken care of the things that are coming later, but this is all that has to be done in this one step. So we start with the common case, and then after we have dealt with the common case, then we think about those special cases of how do we get started and how do we finish. So how would we set ourselves up here for success, set ourselves up for our code working, there we go. How would we set ourselves up for our algorithm to work so that f and n are appropriate values when we begin computing with n being equal to 5? Well, n is going to be 5. So what should we set f up to be so that we'll be able to multiply it by whatever this loop says? So we're going to be able to multiply it by 5 and have the result be correct, and then move on and multiply it by 4, then move on, multiply by 3, etc. Right, so we want f to start as 1. If we had a problem where we're adding up a bunch of things, maybe the result should start as 0. But because we're multiplying a bunch of things, we should start as 1. Good. So here is some pseudocode that we can use. Now, pseudocode is something that, expresses an algorithm, expresses your intentions for the algorithm, it shows the logic of what it is that you're trying to do, but it doesn't have so many picky rules about syntax and things as programming languages do. So pseudocode is often a really helpful next step once you've figured out how this thing approximately works. Well, if you can express it in pseudocode, or if you can express it in a flowchart, those two things are kind of equivalent. They're both ways of showing what is the logic I want my program to follow without having to worry about the details of, oh, did I remember to put all the colons in the right places, like a programming language would require. So our pseudocode here is, and the other special case is, when do we know we're done? How do we know we are finished with this algorithm? Well, as long as n is greater than 0. That's how we know we're going to continue. So when n gets down to 0, then I guess we can be done. So our pseudocode is going to say, first of all, let's initialize f to be 1. Then as long as n is greater than 0, we'll update f. So f will become f times n, and n will become n minus 1. And when we're all done, then f is our factorial value. And so, having expressed a solution, so notice, by the way, I designed the algorithm without doing any Python. I didn't write any C++, Python, Rust, Go, Scala. I didn't write in any of these programming languages. I just figured out the algorithm and I expressed it in pseudocode. Or you could equivalently express it in a flowchart instead of pseudocode. Figure out the algorithm first and then write the code. So it's kind of like you want to design a bridge before you build it and not get halfway through the building and say, boy, I wish we had designed this thing. When we are writing code, it is really easy to merge those two phases together of designing things and implementing things. And there's a degree to which you can't do good design without a little bit of implementation to test things out sometimes. And so there's not a hard and fast distinction, like you have to do all the design and then all the implementation, but it is really helpful if you can have a design artifact like a flowchart or some pseudocode that expresses what you mean for the code to do, and then separately have an implementation artifact, because then you can check the problem against the design, and you can check the design against the implementation. So if the implementation doesn't work correctly, if it doesn't give you the right answer, you don't just say, oh no, I've got a bunch of code and I don't know if it works or not. You can check it against something. You can check it against the design. And so that's a really, really helpful thing. So I would definitely encourage you, whenever you're solving exercises that get any more complicated than the really trivial ones we've seen so far, as we get into more interesting, more complex exercises and assignments and things, I really encourage you to express, figure out the problem, maybe try to solve it a couple of times by hand, then ask yourself, what did I do there? How did I actually solve that problem? Express that in a flowchart or pseudocode or something. And then once you've done that, then say, how can I turn that pseudocode into Python? Because you're going to see converting that pseudocode into Python is going to be fairly trivial. Let f equals 1, well, that will look like f equals 1. As long as n is greater than 0, well, that's going to look like while n is greater than 0. And the other statements inside of there are basically going to look the same thing. So your pseudocode and your Python should almost look the same when you're done, except the pseudocode has fewer rules, and maybe you say as long as instead of while. Well, that's okay in pseudocode. In Python, it's not okay. So we can check that pseudocode against the Python. Someone says, assuming this would be the least complicated way of doing this. Depends what you mean this is. This is about as straightforward a way or as uncomplicated or as efficient a way of computing a factorial as you can get. So yes. If you mean in terms of the process that I'm describing, problem, design, implementation, well, that process is something where, sometimes you can skip the middle phase. If you've got something that's really, really simple, then maybe you can just jump straight into writing code. However, it's good to build that muscle memory of working on problem, then design, then implementation, because as the problems get more complicated, you won't be able to just skip straight from the problem statement to the implementation. So it's good to practice using that design workflow, because for anything more than a trivial problem, it is really, really important. Okay, any other questions? Somebody's typing something. So while that question is being typed and while other people are potentially typing their questions, I will say this would be a really good exercise. You should do this. You should convert this code into Python. And then, yeah, we didn't get to the prime numbers thing, but that's okay. Something I'm also going to point you at is something called Project Euler. So if you go to projecteuler.net, notice it's Euler, not Euler. It's like the Edmonton Oilers. So, and Euler was a famous mathematician. Project Euler is a website that has lots and lots of little problems that are... You won't be able to solve all of these yet, but the first few problems we're now getting to the point where you ought to be able to solve these problems using programming. And they don't refer to any particular programming language, so these are problems that have numerical answers, and they are things that are well suited to programming. So they're good little mental exercises, little problems that you can look at, try to figure out how would I do this for, and here's a good example of, for small values, you could do this by hand. If we list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6, and 9. The sum of these multiples is 23. Okay, I can see how I would figure that out, be able to do that by hand for 10 or 20 or 30. But it says find the sum of all the multiples of 3 or 5 below 1,000. Maybe we're going to need to write a program to do that. And so this is an example of the kind of problems that you can be working on to kind of build that problem solving and turning problem solving into designing algorithms and turning algorithms into implementation, building that problem solving workflow. And that's really, really going to benefit you quite a lot. So I really, really commend Project Euler to you, or other places where you can get problems that you can think of yourself. But working through these kinds of problems and exercises is really going to help you understand what it is that we're doing here. And that's really going to matter as we start to get into the part of the course where we have, for example, midterms coming up. Okay. There was a question, but then never mind, figured out. Okay. Is there a way to group variables? In exercise 3, we had to check if all 9 grades were greater than 55. The only way I knew to do that was to type out each variable that represented each grade. Is there a simpler way to do that? So I'll say at this point, by the way, I mean, it's past 11:50. If you need to go, feel free to go. You can always come back and check this out later, but I will answer questions for another couple minutes if people still have questions. So, yes, that's a great question. On that particular exercise, the only way that we know so far to collect a whole bunch of variables is indeed to say something like my NG1020 grade is, NG1010, and store that in a variable, and then have another variable called NG1020 and store that in a variable, and have another one called NG1030 and store that in a variable. If we want to have all 9 grades available to us, then the only thing we know how to do right now is indeed to use 9 variables. We will learn other things later in the course where we're able to create groups of things. So we can use tuples and lists and other data structures to store multiple things inside of one value. So that's an excellent question. For this particular assignment, you may have been able to do something like, if you wanted to, you may have been able to do something like have a total and then have a loop, and you input 9 grades where you don't actually care what the grades are. It's just type 9 grades, please. And so something like total equals 0, count equals 0, while count is less than 9, total equals total plus input grade, something like that. Now you've got a total and you've got a count, and so then you can calculate things, and for each one you might check, for example, is this grade below 55, and if so, then you could have a variable called promotable that you set to be false if you encounter any grades. Something like, you might have been able to do something like that, but my intention was only that you would do the thing which is a bit tedious, where you have 9 different variables, and you'd say, boy, that's tedious. I wish there were a better way. And there is a better way, and we will get into that. All right, I'm not seeing any other questions coming in, so I guess at this point we can call it a day. I hope that you've all had a... I hope this tutorial has been informative, and if it is, or if it has been, or if it hasn't, do let me know, because I'm used to getting a lot of feedback from students just by like the expressions on your faces. And of course, at the moment, I don't get any of that spontaneous, natural feedback. So the only feedback is like deliberate feedback where you make an effort to decide, I am going to send a message in Top Hat, or I am going to send an email or something. So, we have to be a bit more deliberate about giving feedback, or mention things if you see me in a lab or something. So we have to be more deliberate about feedback. But if you have feedback on how I can make the course work better for you, then I would love to know about it. So, hopefully that's been helpful. And for those who some people have an overflow lab today, and others have labs at other times, and so I might get to see you there. In the meantime, I hope you have a very, very nice rest of your day.